Hello, welcome everyone back to our discussion on the mole index with constraints. Earlier, we discussed the background and the motivation on this topic. We also raised the main question about how the index changed under a constraint. And we also discussed an abstract formulation that addressed the question. So in this video, we'll apply that abstract formulation to study a concrete case of capillary services. So capillary services are the model of interfaces between different fluids. So think about you put two different fluids into a container. So these fluids gonna preserve their volume and also their wetting area. That's why the interface uh, the interface separating these two different fluids are actually equivalent to critical points of the partitioning of a convex body problem that we considered earlier. So let me redraw the picture here. So here, again, omega is some convex body, and sigma here is partitioning of this convex body. And you can think about this is interface between two different fluids. So as we discussed earlier, there are different constraints and different that leads to different optimization problems. Nevertheless, critical points to all these problems are all in the same category of capillary services characterized by the following um, condition. So capillary service here, they are critical point, and they characterized by the following condition. First of all, I have constant mean curvature H, and then also sigma here intersect the boundary of omega at a fixed angle. So this is the characterization of capillary services. Now, recalling the calculus of variation viewpoint, S here is an immersion of some abstract surface, hypersurface sigma into omega. And for simplicity, we can consider omega as the Euclidean ball, b to the n plus 1 inside n plus 1 Euclidean space. The functional here is the area sigma minus lambda, the wetting area determined by sigma. So recall this is constructed using the Lagrange multiplier method. So the second relation can be computed by the work of Barbosa, Ducango, and Eschenberg in the 80s. And you can see here the second relation is actually associated with a symmetric bilinear form. So for this form, take into input function u and v, and gonna produce a scalar number computed by the following formula. So here we have the gradient of u in the product with the gradient of v minus puv. So that is the integration over the whole the interior of sigma, and then minus another integration over the boundary sigma QUV. So the function P and Q here are determined by the geometry of sigma. So the index, now there's no, the index of this the index of this symmetric bilinear form is just the index of this operator in the function space of our smooth function. So here we do not consider any constraint yet. For the type 1 constraint, remember that corresponds to fixing the enclosed volume, and that's equivalent to considering UV with zero average. So again, critical point here, the critical point here are exactly the capillary surfaces that we established earlier, and the type 1 Moore index is the index of this symmetric bilinear form Q subject to the type 1 constraint. So our theorem says that the type 1 Moore index here is equal to MIQ, the index without any constraint, minus 1, if and only if the following PD has a solution. So you have Laplace plus P times U equal minus 1 on sigma. The derivative in the co-normal direction along the boundary of U equal to QU on the boundary of sigma. And finally, the integration of U over sigma is smaller than or equal to 0. So in this statement, eta here is a co-normal vector. So this is in the tangent space, but this is perpendicular to the boundary of sigma. And otherwise, if this system doesn't have solution, then the type 1 Moore index is actually equal to the zero index. So the proof is given as follows, and it's going to be the only proof that you see in this talk. So first of all, we replace the space of our smooth function by the Hilbert space H1 of sigma, and C infinity sigma is dense in H1 of sigma, so it can be shown that this replacement doesn't change any index. Now, the index form, as we saw earlier, so is given by this formula. So the operator associated with this index form is, as you can see in this case, the operator here is given by the following combination. So this is minus Laplace, the Laplace operator plus P acting on sigma, and then the co-normal derivative acting on the boundary of sigma. So this is the elliptic operator associated with this bilinear form. On the other hand, the constraint here is that the integration over the boundary of U must be equal to 0. So this constraint can be interpreted as a linear functional in the following way. So phi here, the constraint here is given by the inner product with a constant function 1 on the over the interior of sigma plus the inner product with the constant function 0 over the boundary of sigma. And it can be shown that phi here is nice because of the Fredholm alternative associated with this elliptic operator. And then we apply the functional analysis theorem. Remember, the functional analysis theorem says that the index is going to be decreased by 1 if there is some element u such that s of u going to be equal to 3, and then phi of u is smaller than equal to 0. So interpreting these conditions using our formulation here, we exactly arrive at the statement of the theorem. So that is the proof of the theorem for the type 1 constraint. For the type 2 constraint, we have very similar statement. So the type 2 constraint is corresponding to fixing the wetting area. So that is to consider UV with 0 boundary average. So critical point. In this case, the critical points are given by the following condition. So here, the mean curvature must be equal to 0, and sigma here also intersects boundary of omega at a fixed angle. So this is a special case of capillary surface. This is the minimal capillary surface. And the type 2 Moore index, again, is the index of this operator subject to type 2 constraint. And applying the very similar argument, we obtain also a theorem relating the type 2 Moore index with the zero index. So the PD system here is slightly different because the constraint here is slightly different. So that's how we can apply our abstract formulation to study the concrete case of capillary surfaces